Hey, welcome back, and we just get into the last part of this week's video lecture. So in this part of the video we're going to look at statically indeterminate beams and shafts. So here a member is classed as statically indeterminate if the number of unknown reactions are greater than the number of equilibrium equations. Okay, so up until now, when you've been doing equilibrium problems, calculating reactions at supports, generally you had the same or fewer unknowns than you had number of equations of equilibrium. But there are of course circumstances where you have more supports than and reactions at supports than the number of equations of equilibrium. So you need extra equations in order to solve for the extra unknowns, and using superposition and deflections is one way that we can solve for those unknowns. Okay, so if we're wanting to determine the reactions on a statically indeterminate beam, then we specify the redundant reactions. We write compatibility equations or conditions. Now you won't know what that is, so we're going to talk about that in this video. So basically all we're doing is looking at the boundaries of supports. So usually what we say is at a support the displacement there is 0. Okay, and we use that to help us to write an extra equation for the unknown at that reaction or at that support. So we use equations of equilibrium to solve for the rest of the reactions. Okay, so one way of identifying statically indeterminate problem is that there's redundant supports. Okay, so these are the additional support reactions that are not really needed to keep the beam in equilibrium. Okay, so let's have a look at what that is. But before we do that, we've got down here the number of the number of redundant supports is referred to as the degree of indeterminacy. Okay, so let's have a look at a couple of examples. So in this first one here, we've got a beam that's built in at end A here at the left hand side, and then on the right hand side we've got a roller support. So as you would know from your previous work, that if we had no support here, this beam could still be in equilibrium. Okay, so here we've got a fixed support. This can support a reaction in the vertical direction, horizontal reaction, and also a moment. So we don't really need this support out here at B in order to keep this thing in equilibrium. Okay, so therefore it's redundant. If we look at the free body diagram, so here we place our support here with the unknown reactions. So we would have a vertical force, horizontal force, and an unknown moment. And then at the right hand end at B here we have a roller support, so we would have an unknown vertical force. So here we've got 1, 2, 3 and 4 unknowns and only 3 equations of equilibrium. Okay, so it's 2D, so we only have a moment equation and 2 forces, force in the vertical direction and force in the horizontal direction. So it's indeterminate to first degree because we have 4 unknowns, 3 equations of equilibrium. 4 minus 3 is 1. Okay, so in our second example here, we have a beam with 4 supports here. We've got a pin support at end A and a roller support at end D. So this is, you'll be familiar with this as your simply supported beam, but here we've got these 2 extra supports in between. Okay, so these 2 intermediate supports are redundant. We don't really need them in order for this beam to be in equilibrium. Okay, so that gives us 2 extra unknowns that we can't solve for using the equations of equilibrium. Okay, so we've got 1, 2, 3, 4, 5 unknowns, and we would only have 3 equations of equilibrium, again because it's a planar problem. So some of the forces in the horizontal direction, some of the forces in the vertical direction equals 0, and some of the moments equals 0. So 5 minus 3 is 2, so statically indeterminate of degree 2. Okay, so our procedure is to identify the redundant support reactions and then replace those with unknown loads. Okay, so where we have a redundant support, we don't know what the reaction is, just put an unknown force there and we'll calculate that as part of the process. So we use the principle of superposition to obtain a series of similarly supported beams. Okay, so like we did in the previous videos where we added up multiple loadings on a beam to get the total deflection, here we're going to do a similar thing to help us find our unknown redundant supports. Often we need to sketch the deflection curve for each beam in order to work out whether it's going to be positive or negative, the deflection at each point. And it just helps us to understand what's going on in the problem. So then we write the conditions of compatibility. Okay, so usually that works out that you're at a support, the deflection is equal to 0. So you add up all of your here, so your principle of superposition, you add up all of the similarly supported beams with all the loads, including the one that has the redundant support, and the deflection at that point will be 0. Okay. Cases where that's won't be the case would be if you have beams sitting on top of each other. So the deflection won't be 0, but the deflection of the two beams will be the same. Or if it's sitting on springs. Okay, so I've got a spring support. You know that the deflection of the beam at the spring support will be the deflection of the spring. And then once we've solved for those reactions at the redundant supports, we can then use equations of equilibrium to find the rest of the reaction forces and all moments. Okay, so here's an example. So we have a beam here with two intermediate supports. So we can see this is statically indeterminate. If we remove those redundant supports and replace them with unknown forces. Okay, so then we'll have the first part of our superposition. So we have the beam with the original loading. Okay, so those two forces will generate deflection at B and C. Then the next one is where we have the force that is generated by the redundant support B. Okay, so that will have a deflection. Don't worry that this is pointing downwards for now. We'll deal with signs later. And then at C, we have our unknown force here, C, Y, and that will also cause the beam to deflect. Okay, so if we consider point B to start with, so for this one here, we have displacement B due to our two forces, and then VB dash, okay, due to the force BY. So that's the force at our redundant support B. And then we'll have a displacement here at B due to the force CY, okay, which is the force at our redundant support C. So that's one compatibility equation. Right? So just going back here, this plus this plus this must be equal to 0, right? Because we have a support here. All right, so point C. Again, point C will have a deflection due to P1 and P2. And point C will have a deflection due to force at BY. And deflection at C due to the force CY. Okay, so here's our second compatibility equation. This deflection plus this deflection plus this deflection. Right, because this is representing where we have the redundant support, that will also be equal to 0. Okay, so from what we did in the previous video, where we looked at calculating these deflections using the standard beam formulae. We can write equations here that will have unknowns. So this equation here will have by and cy in it as unknowns. This equation will have by and cy in it. So we've got two equations, two unknowns. We can solve for by and cy, and then let's go back, and then we can use our equations of equilibrium to solve for the forces at A and D. Okay, so now we're going to get into some actual sample problems. But before I do, I just want to point out that as is the usual case with these PowerPoint videos, parts of the solution just appear. If you prefer to see me go through a worked example step by step, as if I'm writing on the whiteboard, I've got 3 or 4 statically indeterminate problems here at this EduCreations site where I do just that. So I think some of them are recorded live in a tutorial classroom, others I've done in my office. So you can go and check those. I'll also put down in the below the YouTube video the links direct to each of the videos. All right, so let's get into this example. So this is just putting numbers essentially to that first generic case that I showed at the start of this video lecture. All right, so we have a fixed support here for this beam on the left hand side and a redundant support on the right hand side. So these problems in these PowerPoint videos are written and created kind of from our point of view. So we know that it's a statically indeterminate problem, but you as a student coming into this problem, you're not necessarily told that it's statically determinate. You have to work it out. So what you need to do is just look at the supports and say, are there any of these supports that are redundant? Okay, so as I said, this is a fixed support. We don't really need this support here in order for the beam to be in equilibrium. Okay. The other thing you can do is to draw the free body diagram, put in your unknowns, and then count up the unknowns. Now that of course assumes that you've drawn your free body diagram correctly. I've seen a lot of assignments and exam solutions from students where they've drawn the free body diagram, but they've got the free body diagram wrong. And they've drawn a free body diagram that's not statically indeterminate, and then gone on to use indeterminacy procedures to try and solve the problem, which is total nonsense. All right, so it's critical you get your free body diagrams right. Anyway, let's go through the problem. Okay, so as we did before, we're going to break this up into separate load cases. So firstly, look at the case where we've got the loading, and in some cases we would separate this into 2 as well. So we're going to treat this these 2 load cases together, but you could separate this into just the distributed load and just the single point force here halfway along. But we're going to look at them both together. All right, so then the next part of the solution is to replace our redundant support here with the unknown reaction force. Okay, so we just put in here By. So these loadings here are going to tend to bend the beam downwards. This support here provides a force to push it back up. Okay, so if we just looked at this on its own, it's pushing the beam up, but of course we know from compatibility that this, right, or this deflection downwards plus this deflection upwards must be equal to 0. Okay. All right, so taking positive displacement as downward, okay, the compatibility equation says that this minus this equals 0. And these displacements can be obtained from Appendix C. That's just a table that we've been making use of in the previous videos. So here we've got the first one, uniformly distributed load over the beam. So we want deflection at point B here. So that's given here for us. Then we have our load here, so we can see that this is halfway along. So we can see this force is halfway along, so we can use this load case. And we just need to check that our deflection is at the right location. So we want V at the end here, which is what we're given. So at point B here. So total deflection VB will be this plus this for this load case. And then for the redundant support reaction force, it's just a cantilever beam with a force at the end. So this case, so that's just PL cubed upon 3EI. So we can make use of that. So this one, we just put that here, put in the numbers, and we can calculate that deflection. Okay, so our deflection at the end here, B, is PL cubed upon 3EI. So L is 3. So 3 cubed is 27. Right, 27 divided by 3 is 9. So that's how we get to that 9 meters cubed in here. Okay, so compatibility says this plus this is equal to 0. So we just need to put those together and solve for our unknown force By. Okay, so now we can use equations of equilibrium and then draw the shear and moment diagrams. Okay, so I'm not going to go through that step by step. That's revision. You can use these to practice that if you like. But we'll just go on to the next problem now. Okay, so here we have a uniform beam with uniformly distributed loading. And we're asked to determine the reaction at each support and also the slope at end A. So again, if we look at this, is it statically indeterminate? If we took away this support here, we can see this is a simply supported beam. We don't really need this for equilibrium, so therefore statically indeterminate. Okay. Or if we draw the free body diagram, we have an unknown vertical force here, unknown vertical force here, unknown vertical force here. 3 unknowns, only 2 equations of equilibrium. Right? Sum of the moments and sum of the forces in the vertical direction equals 0. So we need that compatibility equation in order to solve for that extra unknown. So what we're going to do to solve this problem is to replace this redundant support with its unknown force. Okay, so that's what we've done here. Okay, so this is what our deflected shape would look like. So now using superposition, we're looking at just the original loading, so it deflects the beam downwards. So that will give us a deflection here at B. And then our second load case will be our redundant reaction force, RB, acting up here, gives us a deflection upwards like this. Okay, so then we know from compatibility that this deflection here, B, plus this deflection here at B due to the redundant reaction force, all of that displacement would be equal to 0. Okay, so let's calculate these deflections. So in this case, we're going to need to use the elastic, or the equation of the elastic curve. Okay, so we need to look up the tables, and this is what we get if we get the right one. Okay, so we just need to put in for x, right, the value for point B. Okay, so B is at 2/3 L. Okay, so we can put that into the equation there and solve for that deflection at B. Okay. All right, so that's what we get for the deflection due to the distributed load. Now, if you look at the redundant, reaction loading, so we have our force here. Well, this is our standard case where the force is not at the center. So X is equal to A, so we want the deflection at this point. Okay, so A here will be equal to 2/3 L, B is equal to 1/3 L, so we can put those into this equation and solve for this vertical deflection here. Right, so that gives us an equation that includes our unknown reaction force RB. Alright, so now using the compatibility equation, remember that at support B the deflection is equal to 0, so this plus what we found on the previous page will equal 0, so we can put that in here. That gives us one equation, one unknown RB, and we can solve for that, and then from statics and our equations of equilibrium we can solve for the other two unknown reaction forces. Okay, so I'll leave you to do that. Okay, so what's noticed is not in this particular solution is the slope at A. Okay, but you would solve for that in exactly the same way that we did in the previous video, where we're looking at superposition to determine deflections. Okay, so another example, determine the reaction forces at A, B and C, and again you should be able to identify that this is statically indeterminate because we have a simply supported beam with an extra support in the middle. Take this away and it could still be in equilibrium. Right. So firstly draw the free body diagram, write equations of equilibrium, identify the redundant support, use compatibility to solve for one of the unknown forces, and that will usually be at the redundant support. Okay, so drawing the free body diagram, this is what we get. So we can see 1, 2, 3, 4 unknowns. This one we can solve for pretty much straight away because there's no horizontal loading. Sum of the forces in the horizontal direction equals 0, so that will be 0. So we're left with 1, 2, 3 unknowns and two equations of equilibrium, sum of the moments and sum of the forces. Okay, so we need more than just the equations of equilibrium to solve this problem. Okay, in this slide we've just gone through the process of applying the equations of equilibrium first, just to show that you can't solve for all of those unknowns. Okay, so we've identified By as our redundant support, replaced it with an unknown force. So now we can use superposition. Right, so we'll have case 1 with the 10 kilonewton force here, case 2 with our 10 kilonewton force over here, and then case 3 is our redundant reaction force. Okay, so using the standard formulae again, we can find for this case where we have a force somewhere along the beam. Right, we have this as a standard case. Now, need to be careful here that we're calculating the deflections at the right location. All right, we can't use that equation that we used in the previous problem. So if we go back, where was that? Right, we can't use this one, right, because that's the deflection at this point, right, underneath the load. We want the deflection over here at the center of the beam, right? So again, one of the mistakes I often see students making in assignments and quizzes and exams is using equations and calculating deflections all over the place and trying to add them together, right, which is of course not correct. All right, so we want the deflection here. So we need to use this equation of the elastic curve, and we need to put in the correct value for x. So in this case it's going to be simple, it's just L over 2. All right, so that's 6, as we can see here. All right, and because the force here is the same as the force over here, then and it's the same distance from the end and the center, then the force at the center here will be the same for the force on, the deflection at the center here will be the same for the force, 10 kilonewton force on the right hand side. Okay, so that's why we've got this equality here. And then for our unknown reaction force, this is a standard solution, PL cubed upon 48 EI. P in this case will be our unknown force By, so we can substitute that into the equation, substitute our length for our beam, which is 12, and we get that equation for our deflection at B. Alright, so now from compatibility, we know the deflection here at B is 0. So this plus this plus this is equal to 0. So we can write that equation and solve for our unknown redundant support reaction By. Okay. Once we have that, we can use equations of equilibrium to solve for the other two unknowns, and I'll leave you to go through that process, or in fact you can use the equations that we got on the previous or the earlier slide. We're also asked in the problem to draw the shear and bending moment diagrams. Again, this is revision from earlier work, so I'm not going to go through that in this problem. You can practice that and check that you get the same answer here. Okay, so that's the end of the video lectures for this week. Hopefully that was helpful for you. And again, don't forget that there's those other step-by-step solution to statically indeterminate problems at my other EduCreation site, and the links down below below the YouTube video. Okay, so look after yourselves, guys. Be kind to each other. Hopefully we're getting closer to being back to normal. Enjoy the lab. Unfortunately, we can't be in labs this week, but the tutors are putting together some videos for you for that. Okay, catch you later. See you in the next video. Bye for now.